Hello everyone, I'm Jonathan and Thomas will be joining us soon. Welcome to this talk entitled Adaptive Tessellation for Catmull-Clark Subdivision. What we want to talk about today is a set of techniques we put up together to accelerate content creation based on Catmull-Clark Subdivision. To start things off, I would like to recall what Catmull-Clark Subdivision is and why it is important for content creation. So Catmull-Clark Subdivision is an algorithm that takes as input a control cage. Control cage is a low poly mesh such as the one shown on the left here. And given this control cage, Catmull-Clark Subdivision will produce the refined mesh shown on the right. If you repeat this process a few times, as shown on the right here, say 1, 2, 3, 4 times, you get a highly detailed surface called the subdivision surface. Subdivision surfaces are a super popular way to author geometry because artists simply need to edit the control cage on the left to produce the rich and detailed geometry on the right. For this reason, subdivision surfaces are supported by pretty much every interactive mesh editing tool. But now if you look at this from a game engine perspective, say Unity, things get a little more complicated. As of right now, Unity does not support subdivision surfaces. This means that if you have artists iterating on game assets, they only have two ways of visualizing each iteration in engine. Either they import the control cage on the left, but this will usually look way too coarse. Either they import the subdivision on the right, but this means loading a super high poly mesh that will take time to load and render. Now, this illustration is somewhat abstract, so let's look at a practical example to get a better idea of what these limitations look like. As our example, we will look at this subdivision surface from Pixar. Imagine you are working on this asset for a game or a movie and you wish to render it in Unity. As this asset is still in development, you want artists to be able to preview it in engine to get a better feeling of how it looks like at any given time. With partial support for subdivision surfaces, you are left with the two options I just mentioned, either load the control cage or load the subdivision surface. Let's look at each option. So here is option number 1. We load the coarse mesh that serves as control cage. Unfortunately, the result is quite far away from what your artist sees in his modeler. For instance, if you pay attention to the teapot on the left, you will notice the lack of detail on the handle. Another issue is visible on the fridge on the right. Some surfaces are intersecting each other. So clearly, loading the control cage is not ideal to get an idea of what your asset looks like in engine. Now here is option number 2. This time we load the subdivision surface. Now note that how both the handle of the teapot and the intersections are fixed. However, the mesh has over 70 million faces and vertices, which leads to many over-tessellated regions. This obviously means poor performances during loading and rendering. So as you can see from this example, options 1 and 2 are far from ideal for devising a fast content creation pipeline. Ideally, you would like to have a better option. And this is where our option comes into play. Meet option number 3, our solution. As you can see, all objects are as smooth as the subdivision surface, but don't produce over-tessellated regions. This is thanks to our adaptive tessellation scheme, which we compute so as to produce a more or less constant triangle per pixel ratio. What's more is that we compute everything from the control cage, which allows to quickly load the asset. In the remainder of this talk, we will describe the set of techniques we use to compute this image. But before getting technical, let's have a look at a quick demo to see how option number 3 performs in practice. Before we start this demo, I want to say that originally we wanted to perform it live during the physical conference. But since we couldn't do a live presentation this year, we recorded it as we would have done it live. This means that what you're about to see is running real time, and we haven't applied any form of editing to artificially boost loading times or frame rates. So please keep that in mind. Okay, so here Thomas has his subdivision surface loaded and rendered in real time in Unity. As he's exploring the scene, notice how our tessellation adapts to the viewing conditions. This allows him to view the scene at steady performances while limiting artifacts such as aliasing. The level of tessellation is controllable in the editor, so you can pick the best trade-off between performance and quality. Now, Thomas will impersonate an artist who is currently working on this asset to ship it for a movie or a game that will be rendered in Unity. To allow for rapid iterations, you would ideally want the ability to do quick back and forth between your modeling tool and Unity. This is precisely what we are going to do here. So here Thomas isn't happy with the shape of his teapot, so he's going to edit it in Blender. A quick application toggle, and now Thomas is in Blender, modifying the topology of the mesh to his taste. Once he's happy with the new shape, he disables the subd modifier and exports the entire asset back to FBX. Note that disabling the subd modifier is important to make sure we only re-import the control cage in Unity. Now, by toggling back to Unity, the asset is reloaded automatically in a few milliseconds. He can thus preview the impact of his work directly in the final renderer instantly. I hope you can easily see how the ability to switch back and forth like this provides huge productivity boosts for content creation. Okay, demo time is over. Let's get technical and detail how we achieve this in practice. Here's a quick overview of what we are actually doing. Our pipeline only relies on Unity's built-in asset importer, from which we compute everything based on the three main kernels shown on the right. We denote these kernels Halfedge Mesh, Subdivision, and Tessellation respectively. Each of these three kernels is based on some work we recently published online or something new we are about to share in this talk. The first kernel initializes our Halfedge Mesh data structure from the data loaded by the importer. As we will show, the Halfedge Mesh data structure lies at the core of each kernel and is thus super important. Thomas will discuss all the details in a few minutes. The second kernel computes the subdivision surface from the Halfedge Mesh. This is based on a recent publication of mine that I will detail after Thomas. And finally, the third kernel computes an adaptive triangulation using the subdivision surface. I will also provide some details during the last part of this talk. One super important property we mention now is that these three kernels are implemented entirely on the GPU with compute shaders. This is the key to making everything fast. And so to finish our introduction, we will simply provide the timings for the kitchen scene we just showed. Here is the timing for the first kernel, which runs in 15 milliseconds on an RTX 3060. This timing measures the time taken to build a Halfedge mesh out of the control cage. Next, we compute the Catmull-Clark subdivision down to a given level. In this demo, we compute 4 levels of refinement. Here is refinement level 1, here is refinement level 2, 3, and refinement level 4. This kernel runs in 88 milliseconds and produces about 280 million half-edges and 70 million vertices. Finally, we compute an adaptive tessellation over the subdivision data, which takes 2.4 milliseconds per frame on average. Okay, so this was the end of our introduction, so now let's get technical. Thomas is going to detail how the first kernel works, then I will come back to talk about the second and third kernels. Talk to you later.
So, hi, I'm Thomas, and as Jonathan mentioned in his introduction, I will explain how to use a Halfedge mesh data structure, which our three kernels heavily rely on. And since this is important, I will start by describing our Halfedge data structure, and then explain how we build it from a more conventional indexed mesh on a GPU. So, our Halfedge mesh data structure uses two buffers. First is the vertex buffer, which stores the 3D positions of each vertex, and then there's the Halfedge buffer, which stores all the topological information of the mesh. At first, the Halfedge buffer may look complicated, but the best way to see it is as an index buffer with 6 integer values per index, rather than just one as were used with index meshes. These 6 integer values store the results of the main Halfedge operators, which are the vertex, twin, next, previous, face, and edge operators. Let's have a look at an example with Halfedge number 1. On the right, Halfedge 1 is drawn as the blue arrow. The vertex operator tells us from which vertex this arrow starts. In the case of Halfedge 1, that's vertex 2. And this is why you have vertex ID set to 2 in the Halfedge buffer on the left. Now for the twin operator, a Halfedge's twin is the Halfedge opposite to it, with respect to the edge that they both span. And here the twin of Halfedge 1 is Halfedge 7, which is why we have twin ID set to 7 in the buffer. Next we have the next and previous operators. These operators tell us which halfedges precede and follow a given halfedge. They are what allows us to loop around the vertices of a face in the mesh. In the case of Halfedge 1, next and previous are Halfedge 2 and 0 respectively, so we store these values in the buffer. Finally, we have the face and edge operators, which tell us which face and edge a half-edge belongs to, respectively. Since half-edge 1 lies on face 0 and edge 4, we store these values in the buffer. That's all there is to this half-edge buffer. So now that we know what a half-edge mesh data structure should store, let's look at how to build it on a GPU. So here we have the same mesh again, 7 vertices and 3 faces, a triangle, a quad, and a pentagon. And we assume that the mesh loader gives us as input a format such as .object, which gives us a list of vertices and a list of indices for the faces. To start converting this classic mesh format into a mesh that uses the half-edge structure, we start by initializing the necessary data buffers. And here we allocate in memory as much half-edges as we have face indices in the index array, so 12 half-edges. And I will progressively show how we can populate this data for all the half-edges. So if we start with the vertex operator, again here we want to store the vertex from which each half-edge originates. And this actually corresponds to a direct copy of the index buffer from the source mesh data. Again, it's important to note that the half-edge data structure is simply a richer index buffer, which stores the ID of the reference vertex plus additional information. The first of these additional values is the face operator, which we can also directly infer from the source mesh data. Then we have the next and previous operators, and I will show you how to compute them in parallel. To do so, we're going to use a bit field. This bit field is shown here in red, and we associate it with a sum reduction tree in blue. This tree structure will allow us to iterate directly on the bits set to 1 in the bit field. We'll allocate the bit field to have as much bits as half-edges to the next power of 2 with some padding. And we start with all the bits set to 0. The first step of the algorithm is to set to 1 the bits that correspond to the first half-edge of each face. And then we compute the sum reduction of the bit field. To do so, we only have to sum the nodes 2 by 2 from the bottom up. And it's this tree which will allow us to identify the different faces and the ID of their first half-edge. We find this first half-edge of each face using a binary search in our reduction tree. It's a bit complex to explain already, but it's very simple. In fact, here's the code we use, and by the way, we do distribute this code online. And so to show how we use that to compute our next ID and previous ID, I'll look at a specific case, the half-edge in red here. And in practice, we compute this in parallel for each half-edge. So here what I'm showing you is the execution of a specific thread that corresponds to the third half-edge. We use the binary search to get the ID of the first half-edge of the current face and of the next face. Here this gives us half-edge number 0 and number 4, which are part of face number 0 and number 1 respectively. This allows us to know how many half-edges are contained in the current face. Then finally, the next ID and previous ID simply correspond to our current ID plus 1 and minus 1, modulo the amount of half-edges in the face. Here for the next ID, we have to loop back to the start of the face, and here for the previous ID, we don't. At the end of this step, we've computed the next and previous operators of each half-edge in parallel. Let's switch now to computing half-edge neighbors with the tween ID. To do so, we'll use a hash map, and we temporarily add a hash ID to each half-edge at the bottom here. And we use as hash formula the red equation here, which is vertex ID plus vertex count times the vertex ID of the next half-edge. This formula allows us to trivially compute the hash of the half-edge's twin, if it exists. And to do so, we simply have to invert the vertex ID and the next vertex ID in the formula. Looking at the half-edge number 5, we have our source vertex, which is 4. And using the next operator, we get the next half-edge, the half-edge number 6 here in blue. And we look at its own source vertex, which is 2. So this gives us a hash of 4 plus 7 times 2. So we compute these hashes for each half-edge in parallel. And then we're going to check whether the hash of the neighbor exists or not. For each half-edge, we compute its neighbor's hash, so the reverse hash. Using our same example, we now have 2 plus 7 times 4 as reverse hash ID. And now we're going to look for this reverse hash ID within the first hash ID array we've already computed. So here we're looking for 30. which does exist in the hash ID array. So we can store as twin ID the ID of the corresponding half-edge, and here that's half-edge number 8. Looking at another example, the reverse hash ID of the 9th half-edge is 33, which does not exist anywhere in the hash ID array. So this half-edge doesn't have a twin, and to indicate that, we store -1 as twin ID. To summarize, in practice, we need 2 steps. One is to generate a buffer with the hash IDs of each half-edge, and then we look for the presence of each half-edge's reverse hash ID in that buffer. We can do that using a binary search after sorting the hash ID buffer, and on the GPU, we do that using a bitonic sort. Now, for the last step of filling the data of the half-edge buffer, the edge IDs, which are required for the Catmull-Clark algorithm. The number of edges in the mesh isn't the same as the number of half-edges. So here, for example, we have 9 edges for 12 half-edges. And this is what requires us to assign a separate edge ID to each half-edge. To do that, we can again use a bit field paired with a reduction tree, but in a slightly different way. Here, for each half-edge, we set the corresponding bit to 1 in the bit field, but only for one of the 2 half-edges present on each edge, the one with the highest ID. Or in the case of a boundary where there's only one half-edge, we simply use that half-edge directly. Once we're done, we get 9 active bits in the bit field, which is as much as individual edges in the mesh. And we can use the same binary search operators as before to map from our 12 half-edges to the 9 edges. This step allows us to guarantee that both half-edges that are carried by the same edge will have the same edge ID. And that's all for converting a classical mesh to a half-edge mesh, all in parallel on the GPU. Our GPU approach gives us an order of magnitude speed up over a sequential CPU approach. And I will now let Jonathan speak about how the Catmull-Clark subdivision steps are computed also in the GPU.
My turn again. I will now describe how we compute the subdivision surface out of the control cage. The way we do so is by relying on an algorithm I published with my colleague Kenneth last year. Here, I will restrict the presentation of this algorithm to a high-level description. If you want to find out more, please refer to my paper and associated presentation, which provide all details as well as some motivation for using this approach over OpenSubdiv. The key insight of this paper is that each refinement step of Catmull-Clark subdivision multiplies the number of half-edges by exactly 4. This is always true, even in the presence of non-quad faces. Based on this observation, we devise a 1-to-4 mapping for each half-edge that we can compute on the GPU. The rule is illustrated on the left for the red, green, and blue half-edges, which split into the 4 new ones as shown on the right. This leads to a simple GPU implementation that consists of 4 compute shaders, each of which rely on the data provided by the half-edges of the input mesh. These 4 compute shaders allow us to compute a single Catmull-Clark refinement step, and so must be invoked multiple times to reach a given refinement level. Let's have a quick look at how they work. First, we have the face point step, which computes a face point for each face of the input mesh. Second, we have the edge point step, which computes an edge point for each edge of the input mesh. Third, we have a vertex point step, which computes a vertex point for each of those of the input mesh. And finally, we have the half-edge step, which produces the topology of the refined mesh. And that's pretty much it. Whenever we load a mesh from our editor, these shaders are re-executed. Note that if you have a static mesh, you will only need to run them once per reload. And if you're dealing with an animated asset, you will need to run the first 3 per frame. That's all for the subdivision kernel, so let's move to the third and final one, the tessellation kernel. Our tessellation scheme builds upon the subdivision data computed from the previous kernel. To compute our tessellation, we initialize carefully chosen triangles that we refer to as bisectors. Each bisector is illustrated here on the left. Our initialization creates exactly 1 bisector for each half-edge of the control cage as follows. We start from the control cage, as shown here along with its half-edges, and then replace each arrow with a triangle as follows. These triangles correspond to the bisectors, each of which references exactly 3 half-edges from the subdivision surface. We determine these references according to a deterministic rule provided on the upper right. Once we have these bisectors, we devise a simple binary rule to refine them. Note that you shouldn't spend time trying to understand these formulas. I'm merely putting them here as a placeholder in case you want to look into the notes we provide with this talk. For now, let's stick with intuition. Here's what the rule looks like when applied recursively. We start from the root bisector and then bisect 1, 2, 3, 4 times. Since the bisection is binary, it can be seen as a binary tree, where each leaf node corresponds to an actual bisector. This allows us to rely on a concurrent binary tree, or CBT for short, to encode the tessellation. CBTs are a data structure I introduced at HPG in 2020 and that we already talked about last year. Here's a quick recap of how they work. A CBT is composed of 2 parts, a bit field, shown in green, and a sum reduction tree, shown in grey. Each bit set to 1 in the bit field corresponds to a triangle in the tessellation, and the sum reduction tree sums all of these bits so that the root node tells us how many triangles we actually have. This allows us to actually bisect each triangle in the tessellation via simple bitwise operation in the bit field. Here, for instance, I decimated the previous bisection once. Notice how the bit field now carries 0 values, shown in orange. And decimating once more yields even more zeros. And decimating one last time gets us back to the root bisector. We can thus see how a CBT can encode the bisection of a single bisector. Now let's see how to encode the bisectors for the entire mesh. To do so, we simply use a CBT for each bisector. We further pack these CBTs within a larger one. In this larger CBT, each bit set to 1 still corresponds to a unique bisector. And the extra upper levels form a larger sum reduction tree that tells us how many triangles we have in our entire tessellation. Note that to build a CBT, we need a full binary tree, so we always need to round up the number of bits to the next power of 2. This results in some wasted space in the larger CBT, but we don't mind because CBTs are highly compressed anyway. Thanks to this larger CBT and a few extra rules to compute the neighbors of each bisector, we can compute adaptive tessellations on the GPU, such as the one shown here. Notice how the triangulation refines around the target while producing a conforming mesh. If you have sharp eyes, you will notice that the CBT at the bottom is updating along with the tessellation. It turns out that the CBT encodes the actual tessellation displayed here, which is the result of me geeking a bit too much, I guess. Sorry for that. Jokes aside, our approach has 2 main advantages over tessellation shaders. First, it relies on compute shaders and support arbitrary polygons. This makes it very general both in terms of input data and hardware. And second, it encodes each bisector as an integer value. This makes it suitable for caching and geometry compression. That's all for the third and final kernel. I hope you have now a good idea of how our pipeline works, and we have now reached the end of this talk.
So, time to conclude. We hope this wasn't too much of an intense ride. To summarize, we've shown that Halfedge-based representations can help speed up content creation pipelines based on Catmull-Clark Subdivision. We distribute both the source code of this project and a demo of its implementation in Unity using the Pixar kitchen scene. We'll provide a link to the demo on the Advances website. As for limitations, we still have several that we could tackle. A first limitation is memory requirement. Since we explicitly store the subdivision surface, the memory footprint grows exponentially with subdivision depth, and you can thus quickly saturate your GPU memory with steep subdivision levels. As an example, using 4 subdivision levels in the kitchen scene requires almost 7 GB of VRAM. In future work, we'll look at whether it's possible to evaluate the limit surface directly without having to store it. We know it's not possible in the presence of semi-sharp creases, but maybe it's fine to drop support for that, as it seems they're not widely used. A second limitation is runtime performance. While our method does allow real-time previews, it is currently way too slow for direct use in video games. This is why we recommend using this pipeline during content creation, although it would also work for cinematics and movie production. We are currently exploring optimizations based on a GPU-driven pipeline to get better performances. And just before closing, I also want to say that what we have presented so far is only a research prototype. And if you like this research, please let us know and we'll try to get it into Unity. So that's it for us. Thank you for listening.